So now we're ready to do section 4.3 of the Bernoulli equation and pressure variation. This again is a fairly short section where we're going to be describing different concepts in fluid flow, a lot of different definitions basically. So let's get into it. Section 4.3, describing flow. Really, this section is about describing various definitions of what we really mean when we talk about uniform flow or steady flow or laminar versus turbulent. And so there are a lot of definitions when we're talking about fluid dynamics of fluids. And so what we have here for our first definition is the difference between uniform and non-uniform flow. We remember that we can specify the velocity of a particle as being its position along a streamline S or a path line and as a function of time. Now when we talk about uniform or non-uniform flow, what we're talking about is actually the fact that the velocity as a function of position is not changing. We're holding time constant, or at least we're not looking at the time derivative. We're only looking at the derivative with respect to S along that path length. And if the position of the particle is not changing as a function of S, then we have uniform flow. If it is changing, we have non-uniform flow. Steady and unsteady flow are really given for all points within a velocity field, but now the partial derivative of the velocities is with respect to time rather than S. And so if in fact the velocity is not changing as a function of time at all points in the flow field, it's just a steady flow, then we have steady, and if it is changing, we have unsteady flow. There's also a table in this section that describes the difference between laminar and turbulent flow. We will talk a lot about this, and so I don't want to belabor this point right now other than just to describe this in a rather basic sense. So first of all, if we look here, we can see that laminar flow is smooth and flows in layers, or what they call laminae. And so that's why it's called laminar flow. It's very smooth flow. Turbulent flow, on the other hand, is very chaotic and unsteady and appears to be random. And but we can see the ramifications of that are that the variations with time of laminar flow can be steady or unsteady, but turbulent flow is always unsteady. The dimensionality of the flow for laminar flow could be 1D, 2D, or 3D, but because we have eddies and basically chaotic motion in turbulent flow, it will always be 3D. In principle, laminar flow can usually be solved analytically or with a computer, and there are many existing analytic solutions. And their solutions are very close to what we can measure in experiments. However, there's no complete theory for turbulent flow. This is a very important thing. There are a limited number of solution approaches for turbulent flow, and it's very, very complex. So many turbulent flows cannot be accurately predicted with computer models, and we can't solve them analytically. We basically cannot solve the equations. And so we often rely on experiments. And we'll talk a lot about this later on in the course when we talk about scaling approaches. And so we will talk more about this, about the difference between laminar and turbulent flow, and we will consider problems in both laminar and turbulent flow later on. But that should give you an idea of where we're headed and what the definitions of these two are. Another concept that's described is the time average velocity. If you have turbulent flow, you can usually express the velocity. We're just looking at the x component here. You can usually express it as a time averaged component, which can be steady, plus a basically a small perturbation or a turbulent part to that, a changing part to that. So turbulent flow can be considered quote unquote steady if the time average velocity is unchanging. And so this is a mathematical technique that's used to simplify dealing with turbulent flow. Finally, we have dimensional flow, looking at increasing dimensionality of flow. And in this case, you might initially think that situation 1 and 2 are not that different, but if you look carefully, you can see that this is cylindrical flow, and really all that we have to describe the parabolic shape of this flow regime in here, the velocity of this, is really we only need the radial direction. And so it's really if this is constant, if this shape of this parabola is constant along this pipe in the z direction, then really it's one-dimensional flow in radius, because any direction you go radially is going to be the same, the flow will be the same. So this is actually one-dimensional flow. In this case, we have two-dimensional flow because it's a square box, and we actually have flow in both the x and y. It's quite likely that in this case, since it is a square channel, that the flow actually in x and y will be equal, unless, for instance, the roughness of the sides of the wall are different or something like that. That might change the actual flow due to in connection with the walls of the rectangular channel. And in this case, you can see that they've added an additional complication in the fact that the flow or the channel is actually getting larger as a function of the z direction. And so in this case, the velocity is a function of 3 dimensions. So basically, we've got one-dimensional flow, two-dimensional, and three-dimensional flow described here. The one other set of definitions is viscous versus inviscid flow. We will talk a lot about viscous flow, and these are forces associated with viscous shear stress. If the viscous shear stress is large enough to affect the dynamics of the fluid particles, then we have viscous flow. And obviously, we're going to be talking about shear stress, tau, and viscosity in these cases. If these can be neglected, if the viscous forces are small and can be neglected, we have something that we call inviscid flow. Flow can get very complicated, and there are a number of terms that are given to various regions. And so in this case, the flow kind of upstream of the cylinder here, where the flow is nice and steady, is inviscid. There really are no viscous forces impeding this flow. It's constant and quite normally behaved. In the case of a cylinder here, we have the flow of the fluid needs to go around the solid object, and we develop what's called a boundary layer. This is a thin layer where viscous forces will be quite important. Somewhere along this object, depending on the velocity of the flow, the relative velocity of the cylinder and the flow, we will have flow separation, where the flow will move along the wall and be close to it, and then all of a sudden it will peel off and peel away from the wall. That is a region of flow separation in these locations right here. And then after that occurs, we will have a wake. The region of separated flow behind a body. And of course, we have lots of experience. For those of us who have spent time on a river, we have lots of experience with eddies occurring behind large objects like large rocks in the flow in the river. This is just a picture showing flow separation, and this occurs when fluid particles adjacent to a body deviate from the contours of the body. And we can see that flow separation. We actually have the fluid in contact right at the nose of this airfoil, and flow separation is occurring right here. You can see that because it is angled at such a steep angle, we have only a very small region where the fluid is in contact with the airfoil, and then there's a large wake region behind it here. Another great video describing how the wind motion affected the Tacoma Narrows Bridge and basically caused it to collapse is a great video of fluid mechanics and how it interacts with a structure. And so this the Tacoma Narrows Bridge collapse is a really dramatic example of a project gone bad. So you might take a look at that video. Just do a Google search on Tacoma Narrows Bridge collapse and you'll see it. So that's all I have for section 4.3, just all these different definitions that we need to make sure we understand as we move forward in fluid mechanics.